Our speaker today is Michael Oru, who is a senior security consultant at TrustWave Spider Labs. He also is a lead core developer for the Beef project. So please welcome me in giving Michael a warm welcome.
Thank you. So, unfortunately, Ty Miller cannot be here, as you can see. He's from Australia. He helped me. He actually developed the shellcode, the custom shellcode that I'm gonna show you later on in the talk. So yeah, he also works in pure hacking. Anyway, we can skip this. Okay, about the talk, we will discuss a little bit about the current situation and traditional browser exploitation vectors. And we will have a small introduction about Beef. How many of you knows about the project already? All right, so we can skip that as well. And we will see basically how we can compromise internal network services from the hooked browser, sending a custom shellcode that we developed. And then, and then a live demo at the end. It will be fun, so don't get bored. So current situation, as you probably know, Greg, good friend, and you also know that usually browser exploits are so difficult to buy, and if you don't have a lot of money, you don't buy a good exploit. Obviously, we are speaking about 0 days. And also, some boxes, for example, if you see how many exploits were chained in one of the latest Chrome 0 days by a Russian guy, Sergey, I think. He was using like more than 5 or 6 exploits to actually compromise the multiple layers of Chrome, because we have different sandboxes for JavaScript, for external plugins, and you need to arrive at the end to exploit the Chrome component itself. It's called Chrome, and the browser is called Chrome. It's fun. So obviously, if you are not like the US government, you are not going to buy 0 days. And or well, US government, because we are in US, but every government. Also, what happens if the victim's browsers are patched? A lot of times, or for example, if the victim use, for example, no script, sometimes no script can also prevent this kind of attacks, because usually the delivery of the exploit code is mainly JavaScript that is probably coming from a different domain, or for example, a malicious applet, or a malicious flash, or a malicious PDF. Also, how reliable are these exploits? Depending if they are weaponized or not, and depending how much did they cost, they could be less or more reliable. And a lot of times, especially nowadays, you have seen how many ways to compromise the machine through Java applets. And for example, if you use Chrome latest version, also unsigned applets that usually runs without requiring user intervention in the other browser. In Chrome, you still need to explicitly allow to run an unsigned applet. So basically, if you're not a moron, you don't get pwned. That's more or less the philosophy. So cross-site scripting. How many of you think that cross-site scripting is lame? Probably many of you, and don't be shy. Anyway, it's really misunderstood. It's actually found in 90% of our application pen test. It's like the second or the third most critical finding we actually have. And usually, I mean, when you need to deliver the report to the client and saying, okay, can I have this is the proof of concept. So you will see, if you click on this link, if you submit this request through BARP, you will see a nice pop-up. And the customer could say, what the fuck? I mean, is this supposed to hurt me? No. All right, so I joined Trustwave in March, and I'm working in London, and usually when I deliver this kind of application pen test and I found XSS, so like 95% of the times, I usually I usually give to the customer a BIF demo recorded like a screencast, screen recording. And usually they really understand the impact because you show, for example, how you can keylog keystroke logging with JavaScript or interfacing with Metasploit or doing social engineering attacks and a lot of other nice things that are not obviously only an alert box. Or, for example, another lame thing like, okay, this request will steal the cookie and will send it to my domain where there is a web server that is parsing the cookie which is arriving from a parameter. I mean, a lot of times, for example, this is not even possible because you cannot read cookies from JavaScript. So anyway, obviously, well, yes, this is a cool slide. Internal server vulnerabilities are sitting there, bored and lonely. So the idea is the following. On the left, you can see Mr. Wade Alcorn, which is the original creator of BIF, still involved, very cool guy. He's actually a very cool guy because he's smart and he's also driving us always with new kind of different research. So in 2007, he was researching something called inter-protocol exploitation, which we will see in the next slide. And he said, okay, now it's 2012, let's see if we can research further and do something cool, improve the research. And then Ty Miller said, okay, I developed a new staging shellcode that acts like a web server. Cool. And then I said, okay, let's put everything together, let's do some research, and let's port everything to BIF, because in theory, the attack should work like on the paper. And in fact, at the end, it worked quite well. So before going on the IPEC and the shellcode, let me introduce a bit BIF. So, well, you said that you already know what BIF is, right? So anyway, the point is that with BIF, you can really finally do post-exploitation for XSS or whatever kind of vulnerability where you can actually inject JavaScript, so even HTTP response splitting, for example, or even a phishing page. So if you can control a page, as we will see later, we will use a phishing page in our demo. So if you can say, victim, please go to this link, which could be an XSS or not, then from the moment that the victim browser is rendering the JavaScript that you are sending, or you are embedding in a page or in a link, from that moment, an asynchronous communication channel is created between the victim browser and our web application, so BIF. And then obviously, as if you were in Ryan Barnett talk this morning, mod security and BIF, he showed a lot of modules that we currently have. We will see also something more later in the live demo. Anyway, we have a lot of categories of modules that can help you, like, for example, if the browser is Chrome, delivering a particular Chrome extension, and then hook the particular Chrome extension that runs in a different sandbox. And so obviously, you can do much more from the Chrome extension itself. Or, for example, integration with Metasploit and other cool attacks on the network that we will use later. There are also a lot of features like manning the browser, tunneling proxy. For example, the tunneling proxy is a pretty nice thing. It was originally researched by Ferru Mavituna, and he created a POC. The point is that a POC was created, like the server-side code was written in ASP, so you had to run on bloody Microsoft software, all right, like IIS. Why I need to install IIS? So I said, okay, let's port it to Ruby. Ruby, the interpreter is obviously cross-platform. Runs on OS X, Linux, and Windows, and BSD without any problem. So at the end, we ported also the tunneling proxy. So the idea of the tunneling proxy is actually that you use an XSS as a proxy. Like you ask to the victim to do some request on the domain where the victim is hooked, and send the response of this request back to you. So you basically open a server-side socket in Ruby, you point your browser to this server-side socket, and then the request that is arriving to this socket is translated in an AJAX request, which is injected in the victim page, in the victim session, and basically she is doing the request for you in the authenticated session that she's currently on. So basically, you don't need to steal cookies, for example. I did also other old presentation about this if you want to know more. So, revitalizing inter-protocol exploitation. So why it's called inter-protocol exploitation? Because the idea that Wade had is the following. There are some protocols like IMAP, SMTP, IRC, SIP, which are, let's say, tolerant to errors. So if you send garbage to the protocol, like if you send a packet with ABC123, the connection is not closed. So this means that the socket is still open, and this also means that in theory, if we send, for example, let's say a post request, the post request headers will be considered like bad commands, but the connection is still open. So basically, after you have the post request headers, you will also have like the body of this post request, which will be text plain and will contain valid command like login pass, for example, in IMAP, and then you can also append there your shellcode. And that will be actually interpreted, parsed, and in this way you can really pawn the service, as we will see later. So yeah, the whole idea is basically this, that the protocol is not resetting the connection if you send some garbage. For example, POP is doing that, and other protocols as well. So it's not that everything is vulnerable. Depending on the implementation, you should check like with Wireshark and debugger. Before showing how the technique works, I would like to explain a bit about the limitation we had. Well, this part was mine. So there are multiple limitations. The first one is obviously that you are, in BIF, we are not doing any kind of magic to bypass the same origin policy. Obviously, if you have a bypass and you want to include it in BIF, it's fine. So like, for example, if you want, like Java, with Java applets, for example, sometimes you can do that, like depending on the version. No, this is, I think, is still not patched. So, for example, if you have, let's say, two domains that are mapped to the same, like two virtual hosts that are mapped to the same IP, in that case, if you do two requests from a Java applet, the same origin policy will not be bypassed, but the point is that you can still send requests to those two domains, and you cannot do that, for example, in normal browser. You can do that in the Java applet because there is like a flow in how they implemented the same origin policy. But anyway, we are not doing any magic, so the point is that when the same origin policy basically says, okay, you can send data, usually, but you cannot read the response if you are doing it cross-domain. But still, the fact that you can send the data, in Firefox and WebKit, you can still do that, so Chrome and Safari. And this is usually enough to pawn services, because you just need to send something, and then this something, to be basically the shellcode, will do actually something else later. And it will also enable normal cross-domain communication, as we will see in a second. Then port banning. Another security feature that every browser is implementing right now, from a few years actually, is port banning. So port banning means that you cannot send HTTP requests to known ports, like port 22, port 143. You get an error like this one, NS port access not allowed in Firefox. So, and that's bad for us, and that's good for security. The point is that on Firefox, if you install an extension, basically the Firefox extension can override everything. And that's quite bad, because there is not some boxing. Some things like the port banning feature shouldn't be overwritable, because this is actually enabling the attack. If this was not possible, the attack was basically not possible. In fact, the whole proof of concept, which actually now is not a proof of concept anymore, is working fine. Is working right now only in Firefox, because in Chrome and WebKit, I still need to find a way to disable the port banding. Then another limitation actually is the HTTP header size. So when you send this cross-domain post request, as we will see later, in the memory of the process that is receiving and parsing this data, obviously the headers will be there as well. So when you write an exploit, you usually have a defined size, a specific size of, I don't know, 700 bytes, 800 bytes, where you can put your junk, your shellcode, and whatever. In this case, you also need to consider the headers that will be there like junk, but will be there. So usually every browser is creating like 400 bytes of headers. And this is obviously a big problem, because if you are playing with shellcode that is bigger than 300 and something bytes, depending on the exploit you are currently working on, it could be a problem because you don't have enough space. So if you see the code online, which is already online because this presentation was actually presented first in RacksCon in Australia last week, there are a few headers that you can override with the XML HTTP request in the XML HTTP request object, as you can see there. Obviously, you cannot override everything like content length, because then you can, for example, do HTTP. You can do like headers injection, for example. Another good thing that is helping us to save some size is actually overwriting the user agent from the Firefox extension, because you can do also that. Then another difference between the original research from Wade and this new technique is that actually we are sending the cross-domain post request with content type text plain. This is quite cool because basically we can have more space for our shellcode, and also we don't need to determine all those bloody boundaries that you need to have in a multi-part form data request. And then obviously after exploitation, you are not back to normal out-of-browser shells. So meaning that as you can use our shellcode, you don't have to drop like a reverse Meterpret reconnection. So the shellcode is actually, so as I said, is a staging shellcode. So we have the stager and the stage. The stager is like 299 bytes, 299 bytes. It's actually a bit more after you encode some bad characters like the null byte, carriage return line feed, depending on the exploit you are, obviously. And the stage is actually a bit more, but it's fine because actually the stage is injected in memory, and the one that needs to be small is actually the stager. And this is actually a good size, reasonable size, especially because for what the shellcode is doing, that is quite complex, the size is quite nice. So what is happening is that the stager, when you send like a cross-domain post request to, for example, port 143 on a machine in the internal network of the victim, the stager is actually setting up, binding a port that you can choose in advance, and then is ready to accept on that port an additional HTTP post request that will be sent a second later to deliver the stage. All right, and the stage, after the stage is delivered, again, port 4444 or the port you like is binded again, and from that moment, the shellcode will actually pipe commands to the operating system and redirecting the output of the command, the command result back in a HTTP response. Now, the good thing is that after, so what we do cross-domain and blindly is actually the stager and the stage delivery. From the moment the stage is running, the shellcode is always replying with access control allow origin wildcard, an header in the HTTP response. And this allows us to So it's basically CORS, right? Cross originator sharing. And this allows us to read the response from those commands, obviously, because we need to read the command results. So from that moment, you have basically like a normal bind shell without authentication right now that is just waiting that you send other post requests with a particular parameter command, cmd equal, for example, netstat, and then the shellcode is returning back the result. We also wrote a Metasploit module that is not called webbind, but it's actually beefbind. This is not committed yet, but the code is ready, so I guess I will do a pull request on Metasploit soon. Instead, all the code is already committed in our GitHub repository. So this is how it looks like in Firefox. So the first one, this one is the stager. So as you can see, for example, we are sending a cross-domain post request on port 143 after port banding has been disabled. And the body of the request is actually containing some valid commands like A001 list. And then in this case, the string for the egg hunter, because I had to write an egg hunter. I had to use the egg hunter technique for the exploit. And then the second one, as soon as this request is received and the shellcode is running, we send the second request, still cross-domain, on the port that we can choose, 4444, with the shellcode again. And yeah, basically that's what's happening. And even if for WebKit now the whole concept is not working because I need to find a way to disable port banding. In fact, if you are sending, for example, if you bind the nmap service on a port that is not banned by the port banding method, this is working anyway in Chrome and Safari. And this is the piece of code that we need to like do a prototype overriding on the XML HTTP request object to create a send as binary method, because it's not a normal method that is implemented in every browser. Firefox is implementing it natively, and you can do that basically in Chrome and WebKit. Another big limitation, took me a while to figure out how to achieve reliable exploitation, was actually the fact that as you are doing everything from the victim browser, you don't know in advance the size of the headers. You cannot query, you cannot say, hey, XML HTTP request object, can you please let me know how many bytes the whole headers will be? So as you cannot know that in advance, what I did is the following. I bind another port, another socket on Beef, on a different port from the one where the hook is served from, in a way that the cross-domain situation is maintained. So basically, before sending the original, the actual shellcode to the target, I send back the same request without the shellcode, with just like 120 bytes in the body. I send it back to myself in Beef. In this way, I can know exactly how many bytes the HTTP headers will be. What I need to do after that is just saying to the JavaScript that is running on the victim browser, all right, the size was, for example, 427 bytes. Obviously, just double check, because the host will be different, obviously. Just double check a few other fields, but then at the end you can have a reliable way to determine how many bytes the HTTP request headers will be. This is quite cool. Well, as you know, I mean, when you write exploits, 1 byte error is enough to have the shellcode not working, or the attack not working, obviously. So this was a necessary thing. So if, for example, a typical structured exception handler exploit with an egg hunter in a non-interprotocol exploitation situation is like that. So like if you see like what we are sending on the socket, so some commands, then some junk, shellcode, then the pointers to next essay, and then at the end the egg hunter. That usually is like 32 bytes with SCAPE technique. And instead, in this situation with inter-protocol exploitation, you have a slightly different case. So you have the HTTP headers first, and you cannot get rid of it, unfortunately. And then you have less junk, obviously, because you actually create dynamically the junk in advance after knowing how many bytes you have for the HTTP headers, obviously. So this will be less than this one. This is how it looks in memory. So if you attach a debugger to, for example, the IMAP service, the exploit was a known exploit. I was targeting IMAP Eudora 6, something like that. There is a public exploit online. I just had to modify it with an egg hunter. And basically, as you can see here, you can see post. So this is the memory of that process. So you can see that the headers are inside the memory post. And on the right, you can also see here that some valid commands are in memory, then some NOP sleds are there as well. And finally, there will be the shellcode. And this is basically the same thing, but with a view from Wireshark. So this is the first reply. We just send a bogus request to have a small reply from the server, from the target. And then this is actually what is sent. So all the headers and commands, NOP sleds, and then shellcode. And this is instead is how, if you sniff the traffic, it's basically how you communicate with the shellcode. So you send another post request with command equal the command you want to send, and then the shellcode is piping, doing like creating some pipes, and then basically sending the command to the operating system, getting the results, and the response will actually be a response with the access control origin wildcard header, so we can read the response, and with basically with the result. At the end, I also developed a small like terminal in JavaScript using a library, and so basically you can define the target in beef, and then as soon as the shellcode is deployed, you can execute like commands from here. So this is like how it is, like the flow of the whole attack. So first of all, you need to trick the user to install a Firefox extension to disable port banning. Otherwise, all those ports that you cannot target are obviously not target. You cannot target them. Then you basically do JavaScript port scanning. Well, you do like you can run the ping sweep module that we have in Beef, which can identify which hosts are alive in the same subnet of the hooked browser. And then you can run on those alive hosts, you can actually run the port scanning module, everything from JavaScript. And you can determine that, for example, port 143 is open. Then you blindly send the stager, obviously blindly, unfortunately, because we are, again, in the same origin policy limitation. For example, this whole attack, in case, for example, we don't have to proceed blindly, only if we find a way, obviously, to bypass the same origin policy. Or, for example, if this attack, as soon as will work in Chrome, you can actually deliver a Chrome extension, a malicious Chrome extension that is allowing cross-domain communication. So you can even fingerprint the service in advance and send the exploit only for the proper service. I will do that for sure soon. So basically, yeah, you send the stage. After you send the stager, then the port 444 is listening. And now the point is that then you send commands. The commands are the command results are retrieved. But the point is that you don't have anymore, for example, like a reverse connection back to your servers. But everything is going through the victim browser. That's the point. So even from a forensics point of view, well, I mean, they will see something bad that is happening from the victim browser itself, right, inside the internal network. Then you can have obfuscated JavaScript, you can have your server in China, whatever, if you are not doing it for work, obviously. And I don't recommend that anyway. Okay, let's see the demo. So in this way, in this case, we are simulating a production environment, right? Where we created a phishing domain called bing.com instead of Bing, and we start beef. Also, WebSockets are enabled by default, so the communication will be quite nice, quite fast. So what happened here is that we are using the RESTful API, because you can programmatically control beef with the RESTful API from a few months. And we are saying to the RESTful API to actually mount a phishing page on the root URL of beef. And we already cloned it. We already cloned bing.com. So now it's going to be mounted, all right? And obviously, we can also access the beef panel on the same domain. And the Firefox browser is the victim, which is going to our phishing domain, which looks exactly the same. Obviously, in the meantime, the clone page has also the beef hook embedded on it. So just to double check if the victim is properly hooked, we send just a simple prompt dialog. All right, so yeah, we can now proceed to do interesting stuff. So first thing, we want to deliver the Firefox extension using a fake flash update. It was developed by Mike Howard, a guy from Australia, very cool module. So we are just gonna send, so when the victim will see the fake, that she needs to update the Flash plugin, when she will click anywhere in the page, a Firefox extension will be delivered. Obviously, she needs to allow the execution of that Firefox extension, but still, I mean, every attack that involves social engineering is basically that. So we select the Firefox extension. Yeah, and this is what the victim sees, right? And install, sure. Then she will click allow. This is coming from our beef server. Then as soon as she will restart the browser, you will see here another hooked browser after we refresh. That's because the Firefox extension is actually overriding the user agent, and so we see it as a different browser. We can, yeah. Yeah, well, this is still to check. Yeah. So this is in fact the pref.js file of the malicious Firefox extension. So the first thing is that we can override port banning with this directive, network security ports banned override. Then we are also overriding the home page and the new tab URL to our phishing domain. So in case the victim went away from a tab, as soon as she opens another tab, she will be in that same phishing domain, so hooked again. And then we are also overwriting the user agent, and we are also enabling Java. In case, like in the worst case, you can probably send the malicious applet. All right, so now we are gonna detect, we are gonna check which hosts which hosts are alive in the victim subnet. We are just doing like, we are just checking like 10 IPs. It usually takes like 2 seconds per IP. All right, so this is a demo. That's why I'm limiting the search for 10 IPs, so 130 to 140. And there is in fact one host which is alive. And we are gonna do a port scan only for port 143 on that host. That is the port that we want to send the shellcode to, the exploit to. And yes, port 143 is open. So this is the virtual machine with Windows XP Service Pack 3 and our vulnerable service up and running. The only reason I'm not doing a live demo is because actually the version of the IMAP service that I'm running there, Eudora, expired, and I didn't have time to remove some stuff from the registry, honestly. It was like a 30 days demo, full working edition anyway. So yeah, there is in fact 143 listening, and that's the machine. So now that we identify that the host is alive, that the port is open, and we are ready, we also injected the Firefox extension, so port banning is finally disabled. We are gonna send the beef bind module. So there are a few parameters here. You can usually leave them as they are, except the host, the port, and you can also play with the delays in case, for example, the client is very slow. You can add some delays over here because there are multiple steps if you look at the source code of that module. And then, yeah. So we are also, in this case, again, for same origin policy limitation, we are not running beef on an IP, but on a domain, and for the same origin policy, they don't match, even if the domain is pointing to the IP, right? So if you don't do that, if you run beef on your spear phishing servers, you need to do that. Otherwise, you will get some errors. So now, this is what is printed to the console of the victim. It's just as a demo, but obviously you get the same information back to beef, as we will see in the module result. So the stager is sent back. Now basically the code is double checking, like calculating the size, the exact size of the headers, and then adjusting the junk accordingly. As you can see here, you can verify that everything is working properly. At the end, the stage is deployed. And you can use also this module, beef bind shell, to send single modules. And as you can see here, we have a new port listening, 4444, which is actually our stage up and running. And instead of using the other module, you can just use the interactive shell. So you just define the target, so the machine where the stage is running, and obviously with the port, because you can change it as you want. And then, as you can see, you execute commands, and then you get the response for those commands, and yeah, everything is working fine. So we did everything from the victim browser, from JavaScript, and without touching at all the file system of the victim server. Yeah, then you can execute other commands, obviously, like move into C and do a dir inside that. Yeah. And the last one to demonstrate that is not a fake, but again, the code is online, you can try it by yourself. I'm just gonna create an empty file. In fact, copy is not working in this way. It's actually expecting a file, but my knowledge of Windows is not the same as Unix. And yeah, and then exec dir, get the result of that. The new file is here. And yes, it is here as well. So And that was it, basically. So, well, you can ignore this last statement because yesterday I was very drunk, and you can see that. You can feel it probably now. And thanks to my colleagues in Trust. And well, any questions? Anything? All right. Thank you for being here.